Good afternoon, students. Today, I'm going to share you one very important topic which we have discussed earlier about the RC coupled amplifier. And we have, already covered how an RC coupled amplifier looks like. So we are very much familiar with this particular circuit diagram where we can see this is a two-stage RC coupled amplifier, right? And also using some kind of concept of hybrid parameters, we have also gone through the hybrid model of a transistor amplifier. So this is basically RC coupled amplifier circuit, and this is basically the hybrid model of this transistor amplifier. So if you can remember that we have these kind of parameters, that this is a kind of input side, and we can say that I1 is the input current, and also for a transistor, for common emitter mode, we can say that this I1, the input current, must be the base current, right? And this is something, the HI, that is the input you know impedance of this particular amplifier. This is HRV2. We know that this is the voltage source. And so this is basically the input side. And in the output side, we know that we have one current source, which is HFI1. So here it is basically the base current, and we can write it as HFIB as well for a transistor amplifier. And this is one output admittance HO. So this is your I2. This is the output current, or we can say for a common emitter configuration transistor amplifier, we can say that this I2 is nothing but the collector current IC. So this is all about the H model of this transistor amplifier, and this is a kind of load resistance which we can attach it later according to our you know circuit. But for the equivalent circuit of this transistor amplifier using hybrid model or H parameters, we can consider this dotted portion. Now the question arises that what is the agenda of today's topic of discussion by using this hybrid parameters, that is basically you know, to deal with the frequency response characteristics of this RC coupled amplifier at various, frequency regions. Whenever we have discussed about the frequency response characteristics, that is the frequency versus gain characteristics and frequency versus phase angle characteristics, then we have discussed that we can consider this frequency response characteristics in three distinct frequency ranges. One is the low frequency range, another is mid frequency range, and the third one is the high frequency range. So basically, today we are going to discuss that how we can establish the gain as well as the phase angle at you know different frequency ranges. That means in the mid frequency ranges, or in the low frequency ranges, or in the high frequency ranges, as we have already observed whenever we have studied the frequency response characteristics of RC coupled amplifier. Now coming to that, I first want to declare that we need to assume certain consideration. That is what? That is, I'm going to, mention that since We are dealing with RC coupled amplifier. So basically, this is a kind of multi-stage amplifier. That means here, as we can see, that this is two-stage amplifier circuit. So basically, based on this particular concept, we can add more than uh, one or two extra at least to become, I mean, to make it this kind of multi-stage amplifier. That means already more than two as well we can form. But here, whenever we are going to derive certain gain and frequency phase, gain and phase angle values at different frequency ranges, we should keep in mind, this is my assumption number one, we should keep in mind that all stages are identical. All stages are identical. The assumption number two, that is, you can see here, this is our, the voltage source, and this is our output admittance. So here, in these, derivations, this HR, E I can write or you cannot write. I am just writing this E to basically denote that this is a common emitter configuration. And this output admittance are so small that they are neglected. That means we don't need to put this HRV2 and HO in the circuit. So circuit will be more simple, right? Now the assumption number three, that is, these are two, hybrid parameters which we have just mentioned. The remaining two hybrid parameters, that is HIE and HFE, these two hybrid parameters do not change with frequency. That means for mid, low, and high frequency everywhere, these two, HI and HFE, these two parameters hold the same value. This will not change. Assumption number four, that is all the blocking capacitors. Blocking capacitors means we know that this is a kind of blocking capacitors, this CE and all these things. So this blocking capacitors, all the emitter capacitors, or you can say bypass capacitors, all these blocking capacitors are very much negligible. Why? Because they have negligible reactance. They have negligible reactance. So if I say this kind of situation, then you can see that we have obtained a particular circuit like this, that we have HIE, we have HFEIB, but we don't have this HREV2 or HOE, that output admittance. Both are neglected, and we have one load resistance because we have one in case of RC coupled amplifier. If you go back and look at the you know picture of the RC coupled amplifier, you can see that we have one load resistance at the output side, or you can say at the collector side. So this is an RL, and after that, this is an RC coupled amplifier. That means automatically this is a first stage amplifier and it will go on repeating. So it will again connected with another input impedance of the next stage. amplification. So basically, this is a kind of, hybrid equivalent circuit of one single stage of RC coupled amplifier. And if you go on building multi-stage RC coupled amplifier, you will just have to perform the you know the working operation by repeating this particular circuit stage by stage, depending on how many stage RC coupled amplifier you require. So this is your hybrid equivalent circuit. Now, if this is so, now I'm going to start the derivation of the gain as well as the phase angle with respect to frequency at different frequencies. So at first, I would like to start the derivation at mid frequency. So here at mid frequency, we need to take one special consideration. That is, if you can remember that we have some coupling capacitors as well in the RC coupled amplifier circuit, which the capacitors which are basically connected at the collector side of each, you know, self bias arrangement, right? So at mid frequency, we need to consider that these coupling capacitors are going to be negligible because this at this particular mid frequency, all the reactance values of these coupling capacitors are very less. So coupling capacitors have negligible reactance value and hence are neglected. Why I am saying so? Because since these capacitors are neglected, that is why you cannot see the presence of the coupling capacitors at the collector side, because all the coupling capacitors are usually connected at the collector side of the RC coupled amplifier. If you need to consider this coupling capacitor, we need to place all these coupling capacitor at the collector side of this hybrid equivalent circuit, which you can see in the you know derivation related to different other frequency regions. So here at mid frequency, the reactance of the coupling capacitors are very negligible, so that is why we cannot you know consider this coupling capacitors in the H equivalent circuit. So basically we are getting this final you know H equivalent circuit of RC coupled amplifier at mid frequency region. Now, since we have got the particular, circuit, now we are going to start our derivation. Now, the aim is first to basically determine the voltage gain. And we know that the voltage gain we usually define as AV and obviously V2 by V1 because V2 is our final output voltage at the output side and obviously V1 is our input voltage. So AV equal to V2 by V1. Let's say this is my equation 1. Now what happens that whenever we have this kind of situation, then we can easily want to determine what is our V1 as well as what is our V2. So here, if you closely observe that this V1 is the input voltage, and V1 we can write that V equal to, in usually, I into R. That means the multiplication of current and the resistance. So by following the similar rule, I can write that V1 equal to IB into HIE, right? So this is your equation number 2. And what is your V2? See, V2 is the voltage drop across this side. So whenever you have this kind of, situation, that means this is your plus, this is your minus, this is your voltage drop. So that means if I say that the voltage drop is nothing but the, current which is flowing across, this direction, because this is your positive polarity, this is your negative polarity. So current must flow through this direction and multiplied by the resistance. Now, coming to the resistance, you can see that here we have two resistance. One is HIE, another is RL. Both are in parallel combination, right? Both are in parallel combination. So automatically we can say that we have one equivalent resistance which we can, determine by solving the parallel combination of these two resistances. So we can write this thing as Req. But what about the current component? This is the resistance component, right? So what about the current component? Current component is some current which is basically flowing across the parallel combination of this RL and HIE, parallel combination of these two, right? You can see that here we have one current source, right? But obviously, the direction of the current source, you can see that this is in the opposite direction of the current which we are talking about to basically produce the voltage drop across this parallel combination of RL and HIE. So, can we write that this is our, current source HFEIB, but this is in the opposite direction of this, because current has to, you know, flow like this. That means from positive polarity to negative polarity. But here the current source, through this current source, current is flowing like this. That means it is in the, opposite direction, right? So I can put one minus sign here, right? To basically indicate that whatever be the current source that is basically, incorporated in the circuit, it has, a 180-degree phase shift of the particular current which has to flow across this equivalent resistance to create this V2. This is my equation number 3. Now, if I get this V1 and V2 at this particular stage, so automatically we can, determine what is my voltage gain. So AV equal to V2 means minus HAVIB REQ whole divided by V1 is IB into HIE, right? Now what is REQ? REQ is nothing but the parallel combination of REQ is the parallel combination of RL and HIE, right? So I can write minus HAV IB, that is RL into HIE whole divided by RL plus HIE, and we have one IB HIE here. So I can cancel out this IIE, IB, IB, and we are getting, the final expression as minus HFE RL by RL plus HI, which is very, very important, you know, expression, which is very, very important expression, that is AV equal to, minus HFE by 1 plus HI RL. Now what happens that whenever we have this kind of, expression, then one thing is very much clear, that we need to comment on the voltage gain as well as the phase angle with respect to frequency. That means at mid frequency, So what we need to do is that we are basically, concentrating on the magnitude of the voltage gain. If you can, recapitulate how we have discussed the frequency response characteristics, then you can, recall that we have talked about the mod AV, right? The modulus value of this AV. So that means we are very much interested with the magnitude of the gain, voltage gain, and phase angle of the voltage gain. So if I take mod of this, then we know that we need to, neglect this minus sign, and we are getting only HFERL by RL plus HIE. This is your gain magnitude of voltage gain, or you can say gain magnitude itself, that is mod of HFE RL by 1 plus, HIE plus RL. So this is your voltage gain, the magnitude of the voltage gain. What about the phase angle? If you can recall that at mid frequency, your phase angle is a constant straight line, and it will denote basically at 180 degree. So can you see that we have one minus sign associated with us, which means that the phase angle is basically 180 degree out of phase by this negative sign. And obviously, the magnitude of the voltage gain also, if you can recall that this particular, the gain versus frequency curve, that is also, a particular straight line, right? Straight line means basically if you change frequency between this mid frequency range, then also you can notice that there will be no change in voltage gain, or in the magnitude of the voltage gain, right? So that is why you can see that here in the expression of the gain magnitude, you cannot see any frequency related term. No frequency related term is present. What is our frequency term? How can we identify that whether any frequency uh, is present in the particular expression or not? We obviously, you know, we obviously look for any term F or omega, but you can see no such term is present in the final expression of voltage gain. So that is why we can say that the voltage gain, the magnitude of the voltage gain, does not depend on frequency in the mid frequency region, and the phase angle is 180 degree out of phase. So it basically justifies what we have, observed during the frequency response characteristics of RC coupled amplifier at mid frequency. Fine. Now moving to the low frequency. In case of low frequency, one particular, change we need to incorporate. That change is whenever we slightly move towards the, low frequency region from the mid frequency stage, we can see that the coupling capacitor, is holding, a small finite reactance, right? And sometimes it may happen that whenever we are going to decrease the particular frequency in the low frequency range, we can see that the coupling capacitors have, a very prominent, reactance value. Since the coupling capacitors are holding, a finite reactance value, then at low frequency, we cannot omit the coupling capacitor, and we need to incorporate in the, circuit diagram. So if it is so, then what could be my circuit diagram using hybrid parameters of RC coupled amplifier at low frequency? The input side must be same. We have no change. We have one IB, that means the base current, which is the input current. Here we have V1. Here we have HIE. This is absolutely all right. Now moving to the output side or collector side, you can say. This is our very own HFEIB. We have one load resistance, because here also, we are uh, following the, the basic considerations that uh, we need to, avoid or omit the HRV2 and obviously the HOE. So we are not, incorporating those two, because those are the, basic common assumptions during any frequency derivations. So basically, I'm not going to incorporate output admittance, but obviously I am going to incorporate the load resistance, which is in the collector side, right? So this is your, first, you can, if you can closely observe, this is the part of the hybrid equivalent circuit of one stage, I can say, self bias arrangement at the collector side. And whenever you have this kind of, load resistance, after that, if you closely observe the basic circuit of the RC coupled amplifier, you can see that here we have one coupling capacitor, right? This is your C. And at low frequency, what we have just told, that the coupling capacitors are having, finite reactance. So basically we need to consider it. So we are going to place it in the collector side. And after that, obviously, again the input impedance, HIE, and this will go on. So automatically here we have V2. See, this particular, derivation has many shades, many layers, right? So that is why I'm going to, tell you step by step that how you can, easily understand what is basically, you know, um, going inside this particular circuit. Suppose I'm taking consideration that one current I2 for this V2, you know, mm, voltage that is basically, flowing in this manner. And I can also, assume that this is the V dash, voltage V dash that has been occurred across this load resistance. And also, since this is a coupling capacitor, so this is a collector side. Now IC is flowing in this way, Fine. Now what happened? See, we know that our parent equation is to find the voltage gain AV, that is V2 by V1, right? This is our main agenda. And we need to, find out what is V1 and V2, you know, uh, in terms of this hybrid parameters. And finally, we are going to replace this V1 and V2 using those hybrid parameters so that in the final expression, we are getting only hybrid parameters and nothing else. So following the same trend, what we have done at mid-frequency derivation, that this V1 is nothing but this HIEIB, because we haven't changed anything at the input side. Now, what about the output side, V2? What about the output side, V2? See, if I say that V2 is what? V2 is the voltage drop across this HIE, right? So automatically V2 must be the resistance at HIE and the current, and maybe the current, whatever be the current component, that is basically, flowing across this HIE in this manner, right? In this manner. Why? Because obviously this is your, higher polarity, this is your lower polarity. Fine. But you can see that this I2 is basically, flowing across this HI. I2 is flowing across this HI because this is the, the situation. If it is so, then I can see, I can, say, or I can write that this I2 is flowing in the opposite direction to what basically the current has to flow across this HI. So I can write this is minus I2, right, in the opposite direction with what this, current component, whatever is, must be flowing across this HI and multiplied by HI. So this must be your V2. If it is so, then our, main curiosity must be in that, sense that we need to focus on now what is my I2? What is my I2? Because we know that at the end, we don't have V1, we don't have V2, we don't have I1, we don't have I2 in the final expression, but only the hybrid parameters. And if requires all the, resistances, that is load resistances RL is here. And if possible, if it requires any frequency component, or we don't have any frequency component. That's it. So now our main agenda must be to replace this I2. So what is my I2? If you go back and look at the circuit, then you can see that this I2 is flowing in this manner, right? So I2 is flowing in this manner across this HI and across this capacitor C as well. So that means this capacitor C and this HI are in series condition, and you can see that this V dash, this voltage drop, appears due to the, due to the flow of this current I2 across this HI and capacitor C. So if it is so, then can we write that this V dash, which is the voltage, appears across this particular junction? This is in respect to, I2, can we write that this is nothing but, see, whenever we are talking about V dash, that means here also this is your positive polarity, this is your negative polarity. So current must be flowing into this fashion, right? But your I2 is flowing in the opposite direction again. So automatically you should write this I2 and the series combination of HI and the reactance value of this capacitor C, which means 1 by j omega C, right? If you multiply j in numerator and denominator both to basically eliminate the j term at the denominator side. So we know that we have 1j or j square omega c, which gives you nothing but minus j by omega c. All we have, you know, perhaps the concept of complex number. So this is a kind of, thing which we will perform. And obviously, from here, you can write what is your I2. I2 is nothing but minus V dash whole divided by Hi minus J by omega C. See, this is your equation number 4. Now, can you see that first you have, you know, expressed this V2 in terms of I2 and hybrid parameters. Now you have expressed this I2 in terms of V dash and hybrid parameters and also the frequency term. Now what is the V dash? So automatically our motto right now must be to again, eliminate this V or, to express this V in terms of something else. So what is your V dash? So this is one particular, way to express this V dash when it comes to the relationship with I2. But we can express this V dash in different way as well. What is that? Now coming to the left hand side of the RL. Now coming to the left hand side of the RL. Please look at this particular circuit very carefully. Now if you look at this V dash here as well, because this is V dash, right? This is your V dash. Now what you have here, you have one current source at your left, which is HFEIB, right? And you have one total, combinations, I mean, of, or you can say the arrangements of all resistance or probably the reactance of the capacitor in such a way that you have a particular arrangements where this RL, this load resistance, is having a parallel combination with one series combination of this capacitor C and HIE. Can you see that? I'm going to explain again. If you try to, you know, express this V dash in alternative way, then you can see that you have, this is a voltage drop. V dash is nothing but a voltage drop, fine. And we need to express this voltage in terms of, current as well as the resistance, right? The product form of current and resistance. So here, whenever you are going to, you know, find out what is your RL, then you can see that this is a particular combination which is the current source, HFIB. But you have, two certain, path. One path is RL, another path is, this particular path, that is HIE and, C. That means obviously we have dealt with this particular, relationship between these two, that this HIE and C, this capacitor, is having a series combination, but obviously this RL must be having the parallel combination with these two, right? So automatically I can write that this V dash is nothing but the product form of this current source and the equivalent resistance of these three, where this load resistance RL is having the parallel combination with the series combination of these two. This is one, observation I can find. The second observation is similarly the same thing is if I say that this is a kind of V dash, that means automatically the current must flow across this inside the circuit, right? Whatever be the equivalent resistance over here, whatever be the equivalent resistance over here, current must flow across this. But here we can see that the current source is flowing exactly in the opposite direction of the current what supposed to flow through the equivalent resistance. So automatically again we need to place one negative sign along with this current source to basically indicate that this is 180-degree out of phase with what is the current supposed to uh, flow across the equivalent resistance. And by following this we can also express this V dash as minus HFEIB and one equivalent resistance REQ. Now this REQ is nothing but the parallel combination of RL, and we know that the series combination of HIE and the capacitor will give us this value because we have just done this. So this whole divided by RL plus HIE minus J by omega C. This is your V dash. Let's say this is your equation number 5. So now you can see that we have only the hybrid parameters, the load resistance, the frequency term, but we don't have any voltage term. We have one IB here, but it's all right. This IB will also, cancel out since we know that this V1 is nothing but HIEIB. So whenever we are going to take this ratio, so automatically this current will also, going to be cancelled. So now we have reached at a point where we can, substitute all the values in equation 1. So now, starting with that part, I'm taking a fresh page. So here, basically, what we had in equation 1, equation 1 was AV equal to V2 by V1. So now I am going to put all these things. So, or I can write this AV equal to, what was our V2? V2 was, first of all, minus I2 HIE from equation 2 and 3, V1 was our HIEIB. So I need to write from equation 2 and equation 3, right? Now what was my I2? I2 was my minus V dash. So minus will be, positive. So basically only we have one V dash by, I'm going to substitute I2 first, V dash by hi minus j by omega c. And along with this, I'm going to write it down what we have here, HIE and HIEIB. So first of all, this HI will be cancelled out. And we need to write that this is from equation 4, right? Now we are going to substitute V dash. What is our V dash? Because I mean, from the last expression, that is the equation number 5, we can write this V dash is again, minus HFEIB. So I'm going to write down first what is V dash. Minus HFEIB into RL into HI minus J by omega C whole divided by RL plus HIE minus J by omega C. So this is my V dash first, right? This is my V dash first. And what we have here, we have another, HIE minus J by omega C, right? And I need to write it down that from equation 5. So now HI minus J by omega C, this will cancel out. And one thing I must, this thing I missed, this, I have to write one IB here. This is the IB. So IB and this IB will be cancelled out. So ultimately, I am getting that this AV is nothing but minus HFE RL whole divided by RL plus HIE minus J by omega C. So this is what I have obtained and I have marked it as equation number 6. Now please recapitulate the frequency response characteristics curve where we have defined two very important terms. One is lower half power frequency, another is higher half power frequency or upper half power frequency. We are dealing with, low frequency region, right? And at the low frequency region, we had lower half power frequency. So suppose we are now very much, concentrating at lower half power frequency. So at lower half power frequency, what we have learned already, we have learned that if I denote that AVL, if I denote that AVL be the, voltage gain at lower half power frequency, then at lower half power frequency, we have already, studied that this AVL must be, 1 by root 2 mod AVM. I can take mod here as well. That means the magnitude value of the voltage gain at lower half power frequency equal to 1 by root 2 of the magnitude of the voltage gain at, mid frequency. So basically we have, learned this expression already. So if we know that, now this from equation 6, we can write that at lower half power frequency, this AV, this AV, I can write as AVL at lower half power frequency. We can write this as your, I'm just, taking this first mod by following this particular, relationship. I'm taking this mod. So whenever I'm taking this mod, automatically I should neglect this negative sign. And I'm just taking this modulus of this value. So modulus of this value means at the numerator side, I am going to neglect this negative sign. But at the denominator part, what we need to do? We are going to take the modulus value of this whole term, where you can see that we have a combination of real terms as well as imaginary terms, right? So, so I must, guess that perhaps we all have concept of complex variables where these are real terms, this is my imaginary terms, and if we are taking the modulus values of a combination of real terms and imaginary terms, we are going to express this as like this: real term whole square and imaginary terms. That means I'm just you know not considering this J, because J is nothing but only the particular term which denotes that the term associated with J is the imaginary term. So I 1 by omega C is basically the imaginary term whole square, right? And what happened that basically if I take this J by omega C whole square, then we know that here we have one J basically. So J square is nothing but the minus 1, and automatically that minus and this minus will become this plus. So basically this 1 by omega C, which is the term is of the whole square, that will basically come in. Now if it is so, then we can write now this angular frequency omega as 1 by 2 pi fc whole square, where obviously I need to mention that omega equal to 2 pi f, right? So this is what we get here. Now, since this is your mod AVL, this is your mod AVL. So basically what we can do is, in the next step, I'm going to take this RL plus HI out of this square root, and we will be having mod AVL equal to HFERL. This is in the numerator side, and I'm going to take this RL plus HIE root over 1 plus, I have taken this RL plus HIE whole square basically outside to the square root. That is why I'm getting only RL plus HIE. And here I will get 2 pi FC RL plus HIE whole square. This is what I'm getting. I'm giving this equation as equation number 7. Now, from mid frequency gain derivation, we have just, determined that this mod AVM equal to is nothing but HFE RL by RL plus HIE. Why should I need this? Because we know that at lower half power frequency, this mod AVL must have one relationship between with this mod AVM by only this mod AVL equal to 1 by root 2 of mod AVM. So I need this final expression where I have only the hybrid parameters and obviously the load resistance. So therefore, if I now take this AVL, mod AVL, or I can write that mod AVM or mod AVL, this ratio, then I can write this is for mod AVM. This is for mod AVM from this expression. This is equation 8. And mod AVL. Mod AVL is in the denominator side. That means HFERL must come here. And we have one RL plus HIE root over 1 plus 1 by 2 pi f c RL plus HIE whole square. This thing. Can you see that HFE, RL plus HIE, all this will be cancelled out. And finally, I'm only getting root over 1 plus, 1 by 2 pi FC RL plus HIE this thing whole square, this thing whole square, here whole square, right? Because I'm taking the whole thing, right? This is a whole square. That thing I'm getting. This is my equation number 9. Now, if FL is the lower half power frequency, because we are dealing the particular gain expression at lower half power frequency. Now, if FL is the lower half power frequency, then this equation 9 can be rewritten as mod AVM by mod AVL. I can write root 2 for this. Why? Because mod AVL equal to 1 by root 2 of mod AVM, right? So I can write root 2 here. And I can write this 1 plus 1 by 2 pi FL. See this F, I can write FL because FL is at lower half power frequency, and at lower half power frequency I am just putting the relationship between this AVL and AVM here, RL plus HI whole square. So this is our equation, fine, where we are putting the relationship between these two, because we are dealing with, you know, the voltage gain at lower half power frequency in low frequency region. And if I say this is my lower half power frequency FL, I should write FL, at the place of F. So if I square both sides, I should get 2 equal to 1 plus 1 by 2 pi FL C RL plus HI whole square, right? I'm taking a fresh page. So basically, I'm getting 1 by 2 pi FLC RL plus HIE whole square equal to 1. 2 minus 1, that will be 1. So basically, if I now, take the square root, then I should be having this only 1 by 2 pi FLC RL plus HIE, that is equal to 1. So if I now then change the side of this denominator in the numerator, then also I will be getting 2 pi FLC RL plus HIE as 1. That means FL I'm getting 1 by 2 pi C RL plus HIE. Can you see that? that FL I'm getting 1 by 2 pi C RL plus HIE. Let's say this is my equation number 10. So if it is so, then now what will be my equation number 9? I want to show you what was my equation number 9. This is my equation number 9. This is my equation number 9. You can see. That means I have 1 plus 1 by 2 pi FC into RL plus HI. And I have just, obtained that FL. I have just obtained that this FL is nothing but 1 by 2 pi C RL plus HI. Then can you see that in the place of 1 by 2 pi, in the place of this 1 by 2 pi C RL plus HIE, I can write FL, right? I can write FL because I have just, expressed FL like that, right? So if it is so, then I'm going to, write down that this equation number 9, yes, that is equation number 9, becomes mod AVM by mod AVL, that is equal to root over 1 plus FL by F whole square. Only this. So we can write that AVL, mod AVL, which basically our agenda of this particular, you know, mm, derivation, that we need to, find out what is our magnitude of voltage gain at low frequency, that is mod AVL, that is nothing but mod AVM whole divided by 1 plus FL by F whole square. Or I can write mod AVM by root over 1 plus tan theta L whole square, where tan theta L equal to FL by F. Therefore, theta L equal to tan inverse FL by F. Now, I am showing you something very interesting from this expression. See, this is the, phase angle. This is the phase angle, right? And this is the, voltage gain, or what you have, find out from here. This is your voltage gain, what you have obtained from here. If you now, just place whatever be the final expression of AVM, you will get the, final expression of AVL as well. That means if you, substitute this mod AVM by HFERL by RL plus HIE, you will get a particular expression, which is basically the, the final expression of gain magnitude. Here, I'm talking about the phase angle. For phase angle, you can see at lower half power frequency, you're getting tan inverse FL by F. Now, FL is what? FL is your lower half power frequency. F is what? F is your natural frequency. So basically, you can see that here the FL is in numerator and F is in your denominator. So basically, FL, the lower half power frequency FL is leading. FL is leading in terms of F. And at F equal to FL, because That is what we are saying, that we are dealing this particular situation at lower half power frequency. That means whenever the frequency becomes the lower half power frequency at f equal to fl, I can write this theta L becomes tan inverse, because right now f equal to also fl, so tan inverse 1. That means that means 45 degree. That means at lower half power frequency, the phase angle is basically, leading by 45 degree. From where? From the mid frequency, you know, phase angle. So what was my mid frequency phase angle? We have just determined that it is a, you know, straight line, which is basically, you know, determining a particular 180 degree phase angle. So basically, at lower half power frequency, total phase shift becomes that 180 degree, that is the, mid frequency phase angle, and 45 degree lead, which means you are getting 225 degree of total phase shift. This is how you can justify that the, you know the magnitude of the voltage gain as well as the phase angle at lower half power frequency, which you have already, studied during the frequency response characteristics of RC coupled amplifier. That whenever you deal with this voltage gain in low frequency region, you will see that the gain of the RC coupled amplifier is basically dependent on the frequency. That is why gain is changing, right? And the total phase shift at the lower half power frequency is 225 degree. So in the semester exam or in the intermediate any exam, you are probably asked to basically prove that the phase angle or phase shift of the RC coupled amplifier at lower half power frequency is 225 degree. So you need to, you know, perform this whole derivation to answer that particular question. So that's all for, today's topic of discussion. So I'd like to, you know, stop this, and hopefully you will enjoy today's lecture, and if any doubt you will find, you can ask me later in the class.